Yes, you can go ahead.
The science of today is the technology of tomorrow. Hello and good morning, everyone. Welcome to the inauguration and launch of IEEE Nanotechnology Council Hyderabad Section Chapter. This day also marks the first IEEE Hyderabad Nano Day. I am Khalid, your host for today's session. If you're an Iron Man fan, you should remember Tony Stark's nanotech suit in the Avengers Infinity War. Ah, what a movie it was. Tony mentioning nanotech has made a lot of people Google it, which includes me as well. The interesting part is nanotechnology is an idea that most people simply didn't believe, but today it can be used to achieve some really cool stuff. Without any further delay, let's begin with the inaugural keynote by IEEE Nanotechnology Council's 12th Technical Committee's Nanomagnetics Vice Chair, who is also a professor at the University of Tennessee, USA. Let's welcome Professor Dustin A. Gilbert. Over to you, sir.
Thanks, Khalid, and thanks, Professor Dustin. And you have been made.
You can see my presentation now, yes?
Yes, Professor.
Excellent. Well, thank you very much for the kind introduction. I'm really excited to be here at the inaugural session of this newest IEEE chapter. As I was introduced, my name is Dustin Gilbert. I'm a professor at the University of Tennessee and the co-chair of the Technical Committee 12 in the IEEE Nanotechnology Council. I figured, being the kind of opening talk, that I'd give a little bit of discussion about what that means, and then nanotechnology and how it's kind of impacted society and the fantastic opportunities and cool stuff that it does for us, and then kind of conclude with some discussion about India's role in the nanotechnology kind of sphere, if that sounds good. So the IEEE as a institution started in 1884 as the American Institute for Electrical Engineers. And since then, it's ballooned to over 400,000 members globally, producing 30% of all material on electronics, electrical engineering, and computer engineering. But as you can imagine, getting 400,000 people to have a common kind of focus or idea is a bit of a challenge. And so IEEE divides itself into 40 subject-focused societies listed here. Now, further, you can imagine there's significant overlap between these various societies. And so, as a consequence, IEEE also made 7 technical committees that were focused on supporting interdisciplinary research that overlaps with several different societies. The technical committee that I'm associated with, and that this new society is associated with, is the Nanotechnology Council. And the Nanotechnology Council supports 23 different societies, including the one that I'm primarily associated with, which is the Magnetic Society. It has also 17 sub-technical committees covering various aspects of nanotechnology, including the one that I am the co-chair of, which is the Nanomagnetism sub-technical committee. The Nanotechnology Council in total sponsors 5 peer-reviewed journals and 11 annual conferences, and is supported by 23 chapters. Now, one of the things I found when I was putting together this presentation that was kind of exciting to me is, if you look at this list, 8 of the local chapters are in India. It's more than any other country in the world. So it kind of speaks to the interest of India in growing nanotechnology as a kind of vector, a focus, a emphasis that they want to grow in. And I think that's awesome, including the new Hyderabad section right here. All right. Now, nanotechnology. This is a map of where all the places are. But nanotechnology can be defined generally as the machinery and equipment developed from applications of scientific knowledge with components on length scales of nanometers. And when you tell people this, they have trouble grasping what 10 to the negative 9 meters really means. And so the kind of classic answer is 1/100,000th of a human hair, but people don't have a good idea of what a 100,000th of anything is. And so the answer I like better is it's 4 to 5 atoms. 4 to 5 atoms, most materials have a lattice spacing of 2 nanometers to 3 nanometers, and so 4 to 5 atoms. Nano engineers thus are designing systems on the atomic scale. They are concerned with length scales of atoms, and that is really a different way of thinking about nanotechnology. Some people say that nanotechnology then began in 1959 by famous physicist Richard Feynman, boldly declaring, "There is room at the bottom." Then the term nanotechnology subsequently being coined by Norio Taniguchi in 1974. And they're both right, but this was not really the beginning of nanotechnology. Nanotechnology, we've been doing it for millennia, we just didn't know it. So you can see it in stained glass. We're mixing different amounts of nanoparticles made of silver or gold, gave you these brilliant colors that people believed were associated with holiness. And it was really nanotechnology that they didn't understand they were doing, resulting in plasmonic resonance that they didn't understand either, that gave them these brilliant colors that they thought were divine. Kind of the most famous example of this is the Liquorius cup, which was made in Rome in 300 AD. You see when you shine light on the front side of it, you get reflection, it's green. But when you transmit light through it, it's red. And that difference has to do with plasmonic resonance of nanoparticles that are distributed within the cup. So micro and nano engineering is really an ancient skill that no one understood until the last half century. Now, the oldest known nanotechnology is actually in India. It was a paper from just last year about some pottery that was discovered in Kiladi in South India. They saw this really dark black paint on some of this pottery. And sure enough, after some investigation of what the surface is, it was single and multi-wall carbon nanotubes on the surface, just like the Fanta black that you see today on kind of these extreme black painted objects. And so there's still not a whole lot of good understanding about how or why this was done. And I certainly wouldn't want to eat off of a piece of pottery with carbon nanotubes on it, but it is a demonstration of the oldest nanotechnology in the world, and it is a century before the Romans made their plasmonic cups. But even before that, animals were using nanomagnetism. So this is a picture of a bacteria that has superparamagnetic iron oxide nanoparticles within it, and it improves its foraging ability. Honeybees, the common honeybee, the way that it describes to its neighbors where flowers are is through dance, but it uses magnetism, little magnetic nanoparticles inside of it, as a compass to guide the other bees in what direction to face. Birds, the reason that they are able to migrate north-south are nanomagnetic platelets inside their brains attached to little nerve endings. These are all examples of nanoscale magnetic materials within animals. And it's kind of trivial to say, but the nanostructure of those iron oxide nanoparticles is crucial. If your particles are too large, then they're ferromagnetic at room temperature, they agglomerate, and then they tend to be pretty hazardous to animals because they clot, and then you get things like strokes. On the other hand, if they're too small, they're effectively non-magnetic at room temperature. And so it's really a Goldilocks principle that you have the perfect size nanoparticles for biological systems. But the first big impact of nanotechnology, I would say, on mankind is data technologies. To give some appreciation for that, you have to understand where data technologies came from and what the alternatives are. So what you might consider data technologies, the predecessor to computers was so-called punch cards. Punch cards were invented in 1890 in the US to respond to the demands for the census. The machines, they were mechanical computers, developed to read and write punch cards, were developed by IBM in the 1920s. So this, of course, IBM later became the computer monolith that kind of drove computer technologies for half a century. But as of 1959, the population continued to grow. The demand for punch cards and data storage continued to grow. And so you can see this is a warehouse with 4 gigabytes of punch cards, and it's just unmanageable. Well, we're kind of lucky because in the 1950s, punch cards were on their way out, and the development of computers started to come around. So this is a picture of the 1956 IBM Ramac 350, a 5 megabyte hard drive that had to be delivered by airplane because it was too large and heavy. It had a recording density of 3 times 10 to the negative 5 megabits per square centimeter, which is absurdly small by today's standards. Now, in parallel to computer data storage showing up, 1947 was the invention of the transistor, which was originally developed for telecommunications, transmission of phone lines, and led to a Nobel Prize. 10 years after that was MOSFETs, and then we're off to the races in 1960 with integrated circuits. So, but this was all microengineering. It's really surprising. If you look at the feature size of electronics, in the 1970s, it was about 10 microns, and you can track it. And it wasn't till the 2000s that we started reaching into the 100 nanometer length scales, which is what the definition of nanotechnology is. And so the nano engineering of computers really didn't emerge until the 2000s. It's a very recent phenomenon. And since then, it's continued to shrink down to the far sub 10 nanometers now. But notice the linear scale, the linear trend in this data set. This is, in fact, Moore's law. Gordon Moore was a co-founder of IBM, and he predicted a doubling of the areal density every 2 years. And so, sure enough, it held true. And in 2000, when we started to transition below 100 nanometers, you can now transition to the bottom graph and see that, in fact, the frequencies stopped going up. So even though we could keep making things smaller, we couldn't make anything faster. The reason for that is that size is not enough to make things faster. In the early 2000s, processor speed stopped increasing because as you made features smaller, the resistance of each feature went up. In addition, you got more features per area. And so these two things gave you this new problem of heat dissipation, that we could not pull enough heat out of our microprocessors to make them go any faster. And that problem still continues to plague us today. And so electronics have now brought us to the nanoscale. We have more processing power, not faster, but more, and as a consequence, have more data. And this can be seen by looking at the data exchange, how much data is exchanged throughout the world every day. And you see an exponential divergence in the amount of estimated global internet traffic shown here. Whereas kind of in current times, we're up at 130,000 petabits or 130 million terabytes per month of data exchanged. It's just a mind-boggling amount of data. To give you kind of a better picture, here is, I like this infographic. It talks about every minute of every day, how much data is transferred. So for example, Google performs 4 million searches every minute of every day. Every minute, Netflix streams almost 100,000 hours of video content. 4 million videos are watched on YouTube every minute. It's just an incredible amount of data, corresponding to 85 gigabits per second of data information. And let's assume you just want to store 1% of that data, just not very much, 1% on 4 terabyte hard drives. You need 18,000 new hard drives a day, corresponding to $1.8 million, just to capture that small sliver of the global data spectrum. And speaking of 4 terabyte hard drives, recall from the picture I had in the beginning that what 4 terabytes of punch cards looked like. It was a warehouse. And so when you're talking about 18,000 of them, it's just an unimaginable volume of data. But lucky for us, commensurate with the increasing computational power that led to all this new data, we also had rapidly increasing data storage technologies. So the red line here represents flash memory data density, and that more or less corresponds to the feature size that we're able to achieve. While the black line corresponds to hard drive recording density. You see it's slightly higher. Hard drives tend to have a higher recording density than solid state media, but they tend to have other problems with, for example, mechanical devices. But you can see, at least when this graph was made, we were topping out at about 1,000 gigabits per square inch, a enormously high density. Recall the RAMAC was 2.3 times 10 to the negative 7 gigabits per square inch. So we've increased our data storage capacity by 10 to the 10 over this time frame. It's really pretty incredible. But the key to keeping up with nano engineering in terms of electronics was nano engineering itself. That is, developing hard drives that were infused with nanotechnology in order to make them record at high enough density to save all the data that we need. So the first of those, the most well-known one, is certainly the GMR sensor. A GMR sensor is a tri-layer of cobalt, copper, nickel, cobalt, where you have a RKKY interaction between the top and bottom layer through that copper that oscillates with thickness on the order of fractions of nanometers. And so you have to have control of your copper layer on the order of less than a nanometer. And this was a phenomenally demanding technology, but it worked out, and it allows the resolution of very, very small local areas, so we can in fact read the data bits as they go by. The next nanotechnology is recording the recording material, that improving and controlling the granular structure of the magnetic recording media allows recording high fidelity data bits, so we can in fact record now the small areas. And the third one is the read head, which I don't think is usually given enough appreciation. It's a mechanical engineering thing, but it skims along the surface of the disk at 5 nanometers away, traveling at 40 meters per second. So the analog of this, if you want to do out the calculations, is if you're traveling along with your hand, maybe 1 millimeter above the surface of a road, traveling at 800 kilometers a second. It is a phenomenal piece of mechanical engineering. So between these 3 nanotechnologies, hard drives have allowed us to keep up with the increasing nanotechnology in electronics. Now the problem has become that we've made our magnetic recording materials too good, that it has become exceedingly stable, which is necessary for the high density, but it's so stable that we can't write to it. And so the solution that we've come to is what's called heat-assisted magnetic recording, where you take your data plate and you heat it up before you write to it, and then write to it and then let it cool. So it adds a whole new level of complication, where you have your GMR head here on the left, a recording yoke here on the right, and the pictures are always drawn with a laser shooting through it, but lasers don't work. We all know that the limit of a wavelength, lambda over 4 for any laser, is about the limit of your resolution. You hit diffraction after that. And so in order to write a data bit, which tends to be on the order of 20 or 30 nanometers in size, you can't do that. And the way that they get around it is what's called, is again, a plasmonic resonator. The same science and technology that people had been doing for 2 millennia that they didn't understand until so recently, that if they have a metallic disk that is in a resonant volume for the wavelength of light they're illuminating with it, it absorbs the light and converts it to effectively a plasma that then they can focus the heat down onto very small regions of this data, so of the data recording disk. And so you can see in the picture here that lollipop shape and the magnetic recording layer, granular magnetic recording layer immediately underneath it. Plasmonics is absolutely not my field, but you are all very lucky to have 2 experts in plasmonics there today to give talks. So that's very exciting and very cool technology. But as time has rolled on, we kind of have a persistent need to continue pressing it. And so new nanotechnologies have developed, and I think one of the most exciting ones are these so-called memristors. So memristors are 2 metallic layers spaced by an oxide layer. So in this picture, you have a metallic wire running from upper left to lower right. Then you deposit oxide crossbars and a metallic capping layer. By applying a voltage between the 2 metallic layers, you generate an electric field that can draw the charged ions in the oxide together to form filaments. And so these filaments have, of course, a different resistance, typically much, much lower than the oxide itself. So once these filaments form, the resistance between the 2 metallic plates drops, and so you can record data bits as the formation and destruction of these filaments. It is low power, it's non-volatile, and its electric field-based control of resistance that you can use then for computations or data storage technologies. But when you move ions into a metal and around a metal oxide, you don't just change the electrical resistance. In fact, that's probably the most benign thing to change. Ion reactions really change virtually every property of a material. And so let's try something else. Optoionics. Optoionics have the exact same structure. You have a gold capping layer, a magnesium underlayer, and an oxide layer between the 2. By applying an electric field between the 2 metallic layers, push hydrogen taken from water decomposition on the surface of the gold into the magnesium. And as you do so, you make an intermetallic that's clear, and its color changes with the density of the hydrogen. So you can see in this picture here, as you increase the voltage or the thickness, which corresponds to decrease in hydrogen density, you go through the whole spectrum of colors. So this is very similar to the memristor, but now instead of changing resistance, you're changing the optical properties of the material. It's again low power because you're driving no current. It's non-volatile because you remove ions and they tend to stay where they are. And so it's a very powerful technology for now coupling and controlling optical properties with electric fields. But that's not the only property that you can change either. Resistance, optical. How about magnetic? Absolutely, same structure. Gold capping layer, and now instead of magnesium, you use a magnetic material on the bottom, in this case, cobalt. Thin layers of cobalt have a very special property that the magnetic moment points in the out of plane direction when they're very thin. By applying a voltage between the gold and the cobalt, you push again hydrogen from decomposed water on the gold surface through the gadolinium oxide layer and into the cobalt. So you can see the three hysteresis loops here, as grown, as perpendicular SHB, and as a nice hysteresis loop. When you push some hydrogen into it, it becomes effectively reversible in the out of plane direction. And if you reverse the voltage, you pull that hydrogen back out and it returns back to its original state. You can do this over and over and over and over again. And you can see as you change the voltage, you change the magnetism every single time. So this is now low power, non-volatile control of electric field control of magnetism. And this technology in particular is very powerful because it marries electronics, which we've spent half a century developing, to spintronics. Spintronics are, I would say, one of the potential future technologies. They are an analog to electronics that uses magnetism and spin rather than charge. The benefit being that the transmission of spin information doesn't have dissipation and so doesn't have energy loss, and so it has the potential to be much faster and lower energy than traditional electronics. Recall also that energy dissipation and energy is the kind of limiting factor in current microprocessors. So if we can make spintronic-based microprocessors, we can push ourselves beyond our current limits. Also, the spin diffusion length, kind of which defines the scales of spintronic devices, tends to be less than 100 nanometers. And so all spintronic devices are inherently nanotechnology. And you happen to have an expert today in spintronics, and hopefully he'll be giving at least some fantastic discussion about the future opportunities of spintronics and nanotechnology. Recent spintronics work has focused more on topology and topologically protected structures, including the magnetic skyrmion. Now these spin textures, the magnetic moments wrap into this curved circular structure, which gives it a topological protection. That means that you cannot continuously create or destroy these structures. And as a consequence of that, this provides protection against data corruption. And so I have possibilities for that. By then making a strip line of skyrmions, you can use this in a racetrack configuration. A sequence of skyrmions called a bit registry can be pushed along this racetrack and be used for ultra high density recording. As with the previous technologies above, the moving of skyrmions is supposed to be achievable at very low power, and they are non-volatile. So again, we are addressing the power demands that are currently facing our electronic technologies. But if you want to stick with electronics, the cutting edge in terms of nanoelectronics tend to be topological materials. So in these materials, the fundamental symmetries within the material provide a coupling between the spin and the electron momentum. Electron momentum can be effectively thought of as current. And so since we have a half century again developing electronics and controlling currents, we now can couple spin into that using these topological materials, which started off in 2009 with topological insulators and are now kind of going full force in 2015 with wire semimetals. But these have been proposed as kind of the key solid state device technology for coupling qubits in quantum computers. It's the device to make them scalable, so to speak. And again, you have an amazing speaker today that knows a ton about quantum materials and quantum electronics, and will surely give a fantastic discussion about them. Now let me shift gears a little bit, because we've talked a lot about telecommunications. How about nanotechnology in renewables? Energy is definitely a problem that's facing the globe. The diagram here shows the global power demand following an effectively exponential curve. And most of the power that's consumed, we consume it, and eventually it ends up as heat. So how do we satisfy this exponentially growing demand for power, especially when 86% of the power is hydrocarbon-based? Well, the natural answer that most people say is solar technologies, and I love solar technologies. They are a p-n junction, very similar to the transistors that we've developed, that we talked about previously. They are definitely nanotechnology devices, and India in particular has been very strong in developing solar technologies, with 40,000 megawatts of power developed just this last year. So absolutely love that. But the alternative to solar technologies is wind power. And there in Hyderabad, they don't have a whole lot of wind power, but India as a whole has almost as much wind power capacity at 38,000 megawatts as they do solar technologies. And so electric windmills have been around since the 1890s. But why only recently have we seen so many of them? And I'll tell you, the kind of easiest way to answer that is you have to understand a little bit about windmills. You can look particularly at this lower graph on the left, and it shows the power density of the wind versus the height of the windmill. You see, in order to get lots of energy, you need to have a very tall tower. And then you start considering the forces, the physics of windmills. And so you have a tall tower and a seal where the generator is, and you have wind, something like that. And you consider the force, the torque that's acting on this. So the torque is based around the base of the windmill. And so your radius is the height, the force is the wind, which you want lots of force because you want to turn that the big windmill. And so that means you have a really, really large torque, which can be a really large problem. And so the way that nanotechnology has made this possible is twofold. The first, the blades are extremely large and experience a very strong centrifugal force, so they must be very strong. But being connected within the seal, they're at a maximum height, so the biggest R that could possibly be. And so they must be very low weight. So hollow carbon fiber blades minimize this weight while maximizing the structural integrity and allow windmills to exist on the large scales that they do. And now carbon fiber is really a micro technology and it's been around for a long time. So this couldn't be the technology that's responsible for making us have windmills today. The answer is, in fact, the motor, the generator. So the nacelle is at the maximal height, so it experiences the maximal torque, so it can't be too heavy. And advances in magnets in particular have allowed electric motors and generators to be scaled. So you can see here, this is a plot of the energy product of a variety of different magnetic materials over time. And you can see one stands out in recent times, and that's neodymium iron boron, discovered in 1984. And it's been improving with time, even since its discovery. And so neodymium iron boron is good as a motor and generator material, specifically because it has a large magnetic moment and a large magnetocrystalline anisotropy, which keeps it in a particular orientation, even when it's in a magnetic field. But the problem is that little itty bitty defects inside the magnet allow the magnet to reverse prematurely, reverse at small fields, because they're broken areas. And in these defective areas, they reverse, and the magnetic domain that nucleates there starts to propagate out. And so it essentially undermines the anisotropy, which is what gives neodymium iron boron the large energy product that it has. And so sintering to get rid of these defect areas can certainly help, but any material scientist will tell you that sintering materials doesn't get rid of every defect. It gets rid of some, but there are plenty that are still left that cannot just be simply sintered away. And the solution is nanotechnology. So what they found is if you take neodymium iron boron and you break it into small little flakes, little platelets that are on the order of tens to hundreds of nanometers in size, that because they're no longer connected to each other, it's very hard for the magnetic domain to propagate between them. This significantly improved the magnet, but we can still make it better. And to make it better, they take these plateleted, these nanostructured magnets, and they submerge them in liquid neodymium copper, which infiltrates. It percolates into the nanostructure and fills the voids between the platelets. This does two things. The first, it separates the platelets. So now they're magnetically disconnected. So if you have a broken platelet, a defect, it doesn't propagate and destroy the rest of your magnet. Second thing it does is the neodymium comes in and it repairs, it fixes the surface of these magnets. So you end up with fewer defects as a whole. So you can see in the plot in the upper right that doing this improves the energy efficiency by 30% of a material that's already 20 times better than iron. And so your generators can now be more than 20 times smaller than they were in just 30 years ago. And as a consequence, you can build these gigantic windmill towers and get the high energies that you need to justify that kind of cost and expenditure. So smaller, lighter generators make windmills possible, make this renewable technology available. And again, you have two fantastic speakers there that are experts in nanomagnetism and the coupling between interfaces and magnets. I don't know if either one of them are going to talk about neodymium and iron boron, but they're absolutely able to because they know an extraordinarily large amount about the coupling between magnetic layers and interfaces. So very exciting stuff. The miniaturization of electric motors and generators has also enabled other technologies such as electric vehicles, where you can now make smaller electric motors to achieve better efficiency and really make very fast cars. So smaller, lighter electric motors make electric vehicles practical. You also see nanotechnology in a variety of other places and sensors within automotive technologies. So nanotechnology has a place everywhere in these vehicles. Nanotechnology also shows up in a number of consumer technologies. The kind of leading televisions, for example, or screens are these LED televisions, but they still have the same classic technology that everyone has. They use the LEDs as a white light source, but it still goes through a set of crystal displays and eventually a pixel array that is illuminated or not to make the different colors. Modern cutting edge screen technologies use organic LEDs, where each LED is its own color. And those specific colors can then be turned on and off to make different pixel colors. Or quantum dot enhanced LEDs, where again, every single LED has a little quantum dot packet on top of it to make a very specific color. So turning it on and off, turning the LED on and off is what turns it bright and dark, versus the traditional LED screen where it's a liquid crystal display rotating its polarization. Now, quantum dot LED TVs I think are really particularly interesting because they are in fact nanotechnology scaling on the order of less than 10 nanometers, where the nanoparticle is structured in such a way that you experience quantum confinement of electrons, which gives you this specific color. And small changes on the order of a nanometer or less can change the color dramatically. And so this is an incredible piece of nanotechnology that is just kind of cutting edge and brand new and just hitting the industrial scale. You do have a speaker here today that is an expert in organic electronics. Right? Speaking of, I think that his expertise is more in organic transistors, but organic electronics in general are just a cutting edge, awesome new technology. So in addition to telecommunications and energy technology, nanotechnology also shows up in medicine. So classic example is these MRI contrast agents. You can go to the hospital and get these today. The way MRI works is you have a nuclear moment. You switch its orientation with a photon, and it depolarizes, and you look for an echo as it kind of configures it in its original direction. In order to do this, it must exchange angular momentum with the world around it. And so introducing a small fluctuating magnetic field enables this relaxation rate to happen faster and hence increase the contrast. So ferromagnetic nanoparticles, just like in the biological systems of birds and bees and bacteria, they would agglomerate and they don't fluctuate. So they would not work well for this application. But superparamagnetic nanoparticles, we make them so small that the thermal fluctuations dominate their orientation and they're constantly fluctuating around, that is less than 50 nanometers, do work exactly like that. They don't agglomerate, and they can exchange angular momentum with the atoms around it, allowing the NMR to occur faster and increasing the MRI contrast. You can see, for example, right here, the picture on the left is without contrast agent. The one on the right has super paramagnetic iron oxide nanoparticles, and you can see significantly more features. And so for high resolution MRI imaging, this is a technology that's available today. But super paramagnetic iron oxide nanoparticles also show up in a variety of other medical applications. So for cancer treatment, if you take these iron oxide nanoparticles and apply a alternating magnetic field, as your particle goes through hysteretic reversal, it releases some energy, some thermal heat that locally heats the area. Now, when we recognize that most human cells and human pathogens die at about 43 degrees Celsius, if you put some iron oxide nanoparticles right where a pathogen or a cancer cell is, you can apply this AC field and heat it up locally. So you can see exactly this happening here. This is a mouse with a tumor cell on the top, before and afterwards. And where the treated one is in the lower right, the cancer has been killed. So this is a way of treating cancer without any of the nasty side effects of radiation or chemotherapy. If you take the same iron oxide nanoparticles and you attach an antibody to the surface, they can actually target specific cells, including cancer cells, and latch themselves to them. Then if you apply a strong static magnetic field, it is able to drag those cells and remove them from the body. So these are kind of future technologies, but they've been demonstrated in laboratories. And so it is very exciting ways in which nanotechnology is impacting medicine. Another way that already exists also is your body is pretty good at denaturing chemicals in your body. So if you get medicine, it tends to break it down pretty fast, which is why you have to take pills every day if you're sick, for example. But if your treatment is something like an injection, it can be pretty daunting and annoying to go get an injection every day. And so nanotechnology is a way to solve that. They already have these technologies. You can take a drug and encase it in a nanoscale polymer cage that then is able to circulate your body for months and slowly release the drugs that you need without having to go back and get more treatments. And so this again is nanotechnology impacting your daily life already. There's a lot of ways where people are trying to integrate nanotechnology into human sensory to restore things like senses of taste and touch and hearing and sight that are absent. People that got injured, for example, and this are efforts to repair them. So connecting neurology to nanotechnology, and of course, the dream eventually is to have nano and microscale robotics that will one day be able to deliver medicine in a targeted way. And in some ways, we're already there. The picture in the bottom is a nanoscale rocket. That's zinc that reacts with your stomach acid. And it's been demonstrated it can zip around in your stomach, as weird as that sounds. And you have an expert today here that is an expert in nanoscale technology and medical applications. And surely he will talk about some very exciting applications of this. So where does India fit into this whole thing? So in 2000, India generated 2% of publications in nanotechnology. It's a pretty small fraction. But around the same time, India started investing very heavily in nanotechnology, and by 2009, so 9 years later, it grew to 5%. They were number 7 globally ranked in the nanotechnology publications. And then you look just, 7 years later, they've increased the ranking from number 7 to number 3 globally. They produce 8.4% of the nanotechnology publications, and so they are on a strong upward trajectory, I would say. Part of this has to do with the investment from the Indian government. So you see in 2005, they invested $250 million in the nanotechnology mission to just try to grow nanotechnology as a domestic product. And I think that is just fantastic and really paying off well. Part of that I think is really fun is that investment partially developed technologies that were then transferred to corporations. That this pie chart here shows a variety of technologies that were developed in the laboratory and transferred to a Indian-based corporate partner. This led to a number of businesses, either Indian native businesses or businesses hosted in India, like FICO that do a whole range of nanotechnology research, development, product distribution, product manufacturing. It is a growing list, and you're lucky again. Yeah, very awesome speaker that's going to talk about entrepreneurial applications of nanotechnology in India. So I think this is actually a really well set up workshop. It has kind of everybody. India's also developed more than 70 formal training programs in nanotechnology, including 3 right there in Hyderabad, both bachelor's, master's, and PhD programs. And India has also spent a lot of money developing a number of government-sponsored facilities, such as their new synchrotron, the Indus 2, their Nanotechnology Center of Excellence there in Hyderabad, and their gallium arsenide facility there, also in Hyderabad, as well as a number of other national labs that really are kind of key to making nanotechnology a accessible thing, pushing research forward. So my hope to all of you is that kind of starting this new chapter of the IEEE Nanotechnology Society in India, I think Hyderabad is an amazing place for this new chapter to be. India is a growing and exciting powerhouse of nanotechnology, and so I think it's great. And I think I kind of want to emphasize to you that you should take full advantage of this. I know you have awesome leaders, but requesting distinguished lectures, attending and hosting summer schools. I went to some of the nanotechnology, nanomagnetism summer school when I was in grad school, and it was very helpful. And so I think it's fantastic. So I guess I should close out. In summary, nanoengineering has been around since antiquity. However, only recently we've had the tools and understanding to work in this parameter space. It is an incredibly exciting time for all facets of nanotechnology, and it's impacting virtually every aspect of humanity that's facing critical challenges. Now, India specifically is accelerating and proving itself as a leader in nanotechnology. And right now is an amazing time to get involved. There are really exciting, interesting problems in science, and it's a fantastic opportunity for jobs and career opportunities in nanotechnology. That's what I got. Thank you all very much for having me again.
Very much. Thank you, Professor. It's indeed an honor. You have done a great work in representing what we have in India and Hyderabad. It's very inspiring, and it's open to questions for the panelists. And I think Professor Subramaniam wants to share something. It's over to you, sir.
I want to thank Professor Dustin. It was really a very comprehensive lecture. And we are extremely happy that we are inaugurating this chapter, and section will cooperate in all possible ways, and we will make it a very excellent chapter. Thank you very much. It was very comprehensive, and how it is so interdisciplinary and covers many aspects. Thank you very much.
Oh, my pleasure. Thank you for having me.
Yeah. Khalid, you can take over. If we have any other questions from the panelists or discussion, or we will move forward. Yeah, so I take this opportunity to thank Professor Dustin, and it's really thankful, sir. It's late night for you, I understand, and the lecture was very inspiring and motivating for this young chapter to flourish. And we have all support from the Hyderabad section as well as from the NTC leadership. Thank you, Professor Dustin. A small token of appreciation, a digital memento, and it will be shared with you. To you, over to you, Khalid. Yeah.
Okay. Thank you, Professor Justin, for a quick intro to nanotechnology. I believe the participants got a good grasp of what nanotechnology is and how it is revolutionizing different domains. Thank you for joining us today. Next, we have the launch keynote on semiconductor nanowires for optoelectronic applications by the chair of IEEE Nanotechnology Council Chapters and Regional Activities Committee, and also who is a professor at the Australian National University. Let's welcome Professor Lan Fu. Over to you, ma'am.
Thank you. Do you mind allow me to share my screen?
Professor, you are now a presenter.
Oh, I can do that. Okay, all right. Can you see that? Okay.
Yes, Professor.
All right. So at first, I would like to warmly congratulate the IEEE Hyderabad NTC chapter formation, and also would like to take this opportunity to thank Dr. Santhosh for your hard work and effort in actually organizing this inauguration event, the Nano Day, and with such a fantastic program. I also look forward to work with you and also your NTC chapter in the coming years to promote activities in nanoscience, nanotechnology research in your region, also across the the whole NTC chapters. So today, I'm going to talk about the research that our group mainly worked on in the last probably 10 years' time on nanowires, on semiconductor nanowires for optoelectronic application. I would like to really thank Professor Gilbert to giving such a fantastic introduction on nanotechnology. Helped me so much in all this background, and also give us such a nice overview of so many different fields that nanotechnology has played an important role. So today my talks really focus on one type of nanostructures and their application for optoelectronics. So before I go to the details, I'd like to first thank my colleagues. So the work I'm going to talk about is really a collective effort over the past many years from many past and current group members in this work, including students, my colleagues, and some professional staff actually helping with nanofabrication in our university, my collaborators across the world, and also the financial support from the Australian Research Council and facility support from Australian National Fabrication Facilities. So our group is called Semiconductor Optoelectronics and Nanotechnology Group. We're basically a very close collaboration from three senior colleagues, Professor Chandrapati Jagadish, Professor Hota, and myself. So we, three of us, working at different areas of nanowires, and but overall we're working with 3-5 compound semiconductor-based nanowire and optoelectronics in lasers, LEDs, photodetectors, and the solar cells that cover broad range of wavelengths from blue to all the way terahertz. So in this talk, I'll first give you a very brief introduction on why I would like to work with 3-5 semiconductors, why nanowires, why they're great for optoelectronics. And then I'll mainly focus on one particular type of 3-5, which is the indium phosphide nanowires, and how we actually synthesize them, and how we characterize them and make them for different device applications. Then I'll mainly focus on the recent work we actually been focusing on developing the synthesis of the multiple indium gallium arsenide indium phosphide quantum wells in nanowire structure and their application in LED and photodetector applications. So we all know, we're probably all very familiar with optoelectronic devices. We all used or have been seeing around us LEDs, lasers, photodetectors, and the solar cells. So all this is a very common optoelectronics that we're actually being used in our everyday life. And more, importantly, that with the development of science and technologies, a new emerging technology in opto interconnects and fiber optics communication, LiDAR systems that used for remote sensing, self-driving car, smartphone, that all use the integrated optoelectronic system. And a lot of them actually are based on 3-5 semiconductor structures. So if you look at the global sort of market for optoelectronic components, there's a really steady increase of the annual growth, and with over 10% growth and projection all the way to 2023. And also, obviously, if we want to keep increasing the functionality, the performance of optoelectronic components and also integrated circuits, what we need is an optoelectronic device that are smaller, cheaper, faster, and with high efficiency. So that's really the motivation that we want to use nanoscience, nanostructure, nanotechnology to actually achieve these goals. So one of that nanostructure. So there are different types of nanostructures. And nanowires is certainly one of them. So why nanowires are so interesting? So basically, we all know nanowires is basically nothing but just a small sort of wire structure that has a nanometer scale. But the interestingly is because of this unique one-dimensional geometry, basically they have very important optical and electrical properties that's actually different from their bulk counterpart. So in nanowires, basically this one-dimensional geometries actually enable that to be able to have more powerful sort of light absorption properties, to be able to basically concentrate incident light to efficiently absorb light in very small volume. At the same time, also it is able to support some local resonance and guiding modes so that you can actually modify the local density of states, optical states, to allow, a good control of the spontaneous emission rate as well as the directionality of the light emitting. So that can be, you can straight away apply for, optoelectronic devices such as lasers, LEDs, photodetectors, and the solar cells. So research in the nanowires is really quite active in the past probably a few decades, and then almost all types of optoelectronic devices being actually demonstrated in nanowires. For instance, LEDs like ranging from UV to infrared, and photodetector ranging from UV to even terahertz, and single and array nanowire solar cells with very good efficiency, and also some nanowire based basic optoelectronic integrated circuits has also been demonstrated. So there's a lot of actually active research in this field. So now I'm just going to give you a little bit sort of share a bit of results that actually is being achieved in our group. So before going to that, I'll introduce you how we actually make nanowires. So basically there are different ways of making nanowires. It's a solution-based technique, chemistry-based, and the technique, another very important technique that used a lot for optoelectronics, actually epitaxial-based, which actually we're actually employing at our university in Australia. So the 3-5 nanowire growth, I'm talking, so nanowires can be also based on different material, but you can base on silicon, that can base on group 2-6, but for the optoelectronics, 3-5 semiconductor is probably one of the most important material. And how to make those nanowires, mainly there are two techniques. One technique is actually, it's just a bit like seeded growth. So you basically put some metals, catalyst, you can spray them onto a semiconductor wafer, such as gallium arsenide or indium phosphide, and then based on a so-called vapor solid, liquid solid growth, basically those little nanoparticle, metal particles can be like a catalyst to promote this one-dimensional nanowire growth. Or you can also make use of some, so obviously, if you're putting those, metal onto the substrate, you basically introduce those kind of foreign impurity into your material, and then sometimes could be detrimental or very bad for your device performance. So people have also demonstrated using of this self metal, so the composition metal of the material such as gallium, by changing, by really tailoring your growth condition, you can also making this formation of some droplets of your self metal of the nanowire at the beginning of the growth, and using that to promote nanowire growth through this WLS technique. But as you can see, those kind of technique, basically you have really random distribution of your nanowire on your sample, which is actually not very desirable for a lot of device applications. So what we like is to have better control of the position of the nanowires, and thereby we actually can have a lot of control in device design, as well as a good uniformity and control across the wafer. So then people actually develop this patent substrate, so using some oxide masks, such as silicon dioxide or silicon nitride, and open nanoscale holes through nanolithography techniques, such as electron beam lithography, and thereby we can open, a little nano-size pattern to promote nanowire growth. So through basically catalyst promoted growth techniques such as WLS. You can also do array growth of nanowires, or using another technique which we call self-selective area epitaxy, where we don't use any catalyst to grow nanowires. So the technique we're using in our group is mainly focused on this selective area growth, where we don't introduce any metals, and then we actually can give a really good control of the nanowire position, size, and uniformity. So this is called SAE growth. So just to look a little bit of detail how we do that. So basically, if you have a substrate such as a gallium arsenide, indium phosphide, or silicon, we deposit a thin layer of silicon dioxide on top of that using PECVD technique. And then using electron beam lithography, we actually, and combined with wet chemical etching or reactive ion etching, we actually can open little holes on top of this silicon dioxide. And then we put it into the MOCVD reactor, the metal organic chemical vapor deposition system, which is a very industrialized sort of reactor for epitaxial growth. And that's the system used to grow a lot of lasers, LEDs are used every day. So we put it into this system and we tune the growth condition. We're able to we put it into group 3 and group 5 precursors inside the growth chamber, and we fine tune the the growth temperature, flow rate, and the material you put it in, and we can actually grow beautiful nanowire arrays from this process. So this is scanning electron microscope image of the nanowires that's grown in our group. This is indium phosphide nanowire, and if you do transmission electron microscope, you can see that they have beautiful crystalline structure of woodsite, and we're able to actually demonstrate the nanowire of this type over a wide range of diameters, from 80 nanometers actually all the way to probably a micron, and with perfect crystalline stacking for 3 structures. If you look at the optical and electrical property of that, so we can see that our SA grown nanowire has actually very low surface recombination velocity, which is a very important property for a lot of optoelectronic application, which means that you don't have a lot of recombination at the nanowire surface, which is always a concern for nanowire device because of the large surface area. And then we have good carrier lifetime. So it's again another indication of important optoelectronic properties. Mobility, very good mobility compared to a lot of WLS grown material. So all this give us a very good starting point to make them into optoelectronic devices. So based on this, the selective area grown indium phosphide nanowire, we're actually trying to make them into different nanowire devices, by making either a single nanowire device to making contact on either side of the nanowires, or we actually can planarize them and making contacts on top and bottom of your structure, and to make them into array nanowire device. So I just give you some very quick glance of the device we made from those indium phosphide nanowires. So first, we actually demonstrate the broadband indium phosphide terahertz detector based on those nanowires. So basically, what we do is that we transfer the nanowires onto our quartz substrate, and through photolithography to make contact on either side of them, so that we can make a bow tie type of antenna, terahertz antenna, as you can see from here. And then we actually put it into the terahertz spectroscopy system in our collaborator at Oxford University. And then we actually demonstrate that the nanowire is able to actually serve as a really good terahertz detector. As you can see from here, is the nanowire detector, and with a very good signal to noise ratio, and also the bandwidth that comparable to the bulk semiconductor terahertz detector. And then furthermore, by actually, trying to really sort of complicate the nanofabrication process, we actually cross contact 2 nanowires, because nanowires have this one this one-dimensional geometry, actually have a very nice polarization response to the terahertz signal. So by doing this is to cross fabrication of this cross type of terahertz detector will actually be able to record the full polarization states of a terahertz pulse. So this is also very an interesting extension of the work that we actually demonstrate from the single nanowire terahertz detector. And then we're actually also showing that in the nanowire structure by putting, during the epitaxial process, in putting doping and create the, PN junction, we're actually able to, through some narrow nano characterization, to look at the PN junction built-in electric field in the PIN structure of nanowire, and thereby to understand the electrical property of the nanowires. And by doing that, we can also design different PN junction profile inside the nanowire structure. As you see from here, by changing different doping profile, we actually be able to shift the building electric field across the an actual junction nanowire, and then we can actually design a solar cell with very good efficiency in those nanowires. So this is actually, and then finally also, I've shown that you can do detectors, you can do, solar cells, and also actually nanowire cells actually by nature are very nice laser structure, because in nature they have a nice facet on the end facet when you actually break them down from the substrate, and thereby you actually, when you pump it, it can form a nice ferroprobe cavity, and then you actually can achieve lasing from those nanowires. So this is a really good demonstration of the good material quality of the indium phosphide nanowire grown by the selective area growth technique, which I've shown here. And then we have also shown that if you actually put the nanowire, place the nanowire in a well-designed nano antenna structure, you're able to actually change the emission to actually focus the emission, make them really more emitting from vertically from the to the top. Thereby you can have more important application as well. So this is really showing again the flexibility of the design and application of nanowires. However, although we have shown its good property from optical pumping, however, to achieve electrical electro-driven light emitting device from nanowire still remains very challenging, and for obvious reasons that if we have just a small nanowire as gay medium, this is not sufficient sometimes for lasing. And also you actually, if we want to making electrical contact, this is always challenging into this material as well, because it's a nano scale and nano fabrication. Any loss introduced by the contacting and localized heating will become very challenging issue for this kind of device. So to solve, to address this issue, firstly, we'd like to, trying to explore to actually implement important structures, quantum structure inside nanowire, which is always used for the planar laser structures or LED structures, the quantum wells, because quantum wells is very important to make use of the quantum confinement effect to actually to increase the efficiency of the lasing and LED structures. So so as I just said, that quantum structures, basically we're making use of the quantum confinement effect, and then also by changing the quantum well material and also quantum well thickness, you're able to actually achieve a broad range of bandgap engineering, so which is also very important for optoelectronics applications. And also, as you can see that, nanowire array itself, it can actually further opportunity to actually making you to be fabricated into micro LEDs. So naturally, you don't have to, through the growth and definition of the nanowire array, you actually can make micro LEDs. And also by tuning the nanowire geometry and properties, you actually can also grade to enhance or tailor the light extraction and the directionality through the nanowire structures. Another important thing is that, we know that indium gallium arsenide and indium phosphide in the quantum wells has already been widely used in laser diode for telecommunication systems. So naturally, it's very important to achieve these wavelengths also in nanowire structure. So this is the nanowire quantum well structure that we'll be actually talking about in the rest of my talk. So a little bit, so before really going to laser, which is much more complicated, also strict device in terms of design to actually achieve. So we're actually starting to look at first how we're actually making light emitting device from LEDs. You are all very familiar with LED. That's actually emitting visible light because you can see them. But you probably didn't realize that infrared LED also have a quite big market, global market, because it have a lot of use application in such as remote control and on-chip integration light source, and for more for the emerging technology like Wi-Fi, infrared LED is also a quite important, interesting candidate for that. So as I mentioned before, that compared to the planar device, which always have issues with the light extraction efficiency. So we know that for the planar LED device, you have to fabricate some light extraction structures to actually enhance that. In nanowire device, so by changing, because the wavelength scale geometry of the nanowires, actually the light extraction efficiency can be enhanced by just design the nanowires with the proper, diameters and pitch size. Thereby, we can actually achieve high extraction efficiency up to 70% based on some simulation work we've done. And next one, what we like to do is actually incorporate a quantum well structure into those nanowires and make them into LEDs. So, so how we do that? The process is pretty easy. So basically, during our nanowire growth, we're starting our growth with a standard indium phosphide nanowire growth, and then we actually insert switching some gas. So basically, we switch off our phosphorus gas line and switching back into arsenic and gallium sort of gas line, so that we actually can grow indium gallium arsenide. So by control the time of the growth, we are able to grow, indium gallium arsenide material sandwich between indium phosphide material. Thereby, we actually create this quantum well structure. So it seems very easy and sounds very easy, but when you actually grow them, when we insert this a few nanometers of indium gallium arsenide into our nanowire structure, what we see is this very ununiform shape. So you might remember that before that beautiful hexagonal shape regular nanowire array we grow from indium phosphide. But this is the image showing that when we just switch in very thin layer of indium gallium arsenide, the whole nanowire morphology has changed. So this is really depends on really because that the formation of indium gallium arsenide. So as we know that the nanowires has multifaceting structures. So what happens that all this faceting, the surface energy are very different for different crystalline material structure formation. And it turns that when we insert indium gallium arsenide, somehow in nanowire structure, he actually wants to form this zinc blende structure, rather than the woodside structure base that we had for the indium phosphide beginning. So thereby, the growth rate along different facets of nanowire becomes different, and then that leads to this very irregular shape of this quantum well nanowire, quantum well incorporated nanowire. So if you do a very detailed TM analysis, we actually see that with the single indium gallium arsenide quantum well inserted into our nanowire, we actually have this sort of three-dimensional quantum well structure formed. You have or you have a component in the axial direction, you have a component in the radial direction. Actually, you have a little corner forming this ring quantum well with always different composition. So it's a very complicated structure. I'm not going to go to the detail of the analysis. So basically, this is give you this basic vision of this quantum well form into the nanowire structure. And of course, because of this complicated quantum well formed, if you look at position dependent photoluminescence study, you can see that photoluminescence coming from this three different quantum well structure: actual quantum well, ring quantum well, and the radial quantum well. Nevertheless, we said, okay, let's just put in some dopant, making it into an LED structure in this one, and see if we can make an LED. And then, as you can see from here, we actually made single nanowire LED by just contacting, the n-junction, n-doped indium phosphide shell and then doing some etching, expose this p-type doped indium phosphide core, and we're actually making LED. We inject current. You can see the electroluminescence coming from this structure, and showing we have a very nice LED, a light emitting at 1.3 micron from this quantum well structure, and showing their really nice LED here. And then, of course, if we actually planarize the whole device and making contacts on the top and back of the sample, we actually can also achieve this array LED from the material. And this is the infrared imaging showing the LED and the light emitting from our single quantum well array LED structure. So that's just showing that nanowires can making really quite nice LEDs. And of course, you can see that we can incorporate further more quantum wells, because more quantum well means to more gain and also better sort of emission efficiency, powerful light emitting from that. But by doing that, the problems that we can see that by incorporating multiple quantum wells, the morphology becomes more uniform. However, we have very short sort of quantum well region forming those nanowires, which actually are limiting the application. So what we want to do is actually how we can really create more uniform quantum wells, not like that one, into our nanowire structure. So as I mentioned before, like the morphology change of the nanowire is really caused by the insertion of this zinc blend 10 zinc blend inclined indium gallium arsenide quantum well layer. So what if we actually create our baseline indium phosphide into zinc blend? In this way, we probably can actually achieve this more uniform growth of the nanowire quantum wells. So so we actually look at the literature, and we found that indeed it's actually 2010. There's a group actually, Professor Fukui's group from Japan already shown that they're able, by tuning the growth windows, they're able to grow indium phosphide, Wuxi indium phosphide, or some mixed phase zinc blend dominated indium phosphide. So we're thinking if we actually can also do that to create a zinc blend base of indium phosphide, we probably can able to actually create more uniform indium gallium arsenide quantum well from there. So my students actually doing a lot of optimization by changing the growth temperature, growth rate, 5/3 rate, and all this. We're able to actually find a good condition to grow this optimized zinc blend based indium phosphides. You can see it's a very nice morphology. And we do some TM analysis and also optical analysis, really showing that this zinc blend based indium phosphide also have very nice optical properties. Although you have quite broad wave photoluminescence coming from different mixed phase in the zinc blend Wuxi, but still the carrier lifetime is up to 1 nanosecond, which is also very comparable to our Wuxi based structure. So based on that, basically it's able to grow now because of the very nice zinc blend base of indium phosphide. We're able to actually incorporate growth of multiple quantum wells up to 40 with very nice uniformity, as you can see from here. And this is a cathode luminescence from those 20 quantum well structure, showing very bright and also uniform quantum well emission. And those nanowires are very, also be able to lace. So if we pump them hard, we can see the very nice lacing achieved at 1.3 micron from those nanowires, 40 quantum well nanowires. So that's we further trying to make them into so we want to see whether we can actually make those nanowires into, again, LED array LEDs. So in this time, we actually create a nanowires, the nanowire array on the same substrate with different pitch size. Because the different nanowire pitch, we actually have different growth of rate of quantum wells. Thereby, we're able to create quantum wells with different wavelengths, as you can see from here. And then you can see thereby from the same substrate, we're able to demonstrate this multi-wavelength LEDs with a very nice electroluminescence, and also we actually can modulate them with relatively high speed to megahertz. In fact, recently we actually do more measurements and we can actually achieve 1 gigahertz actual modulation, which showing that they're actually promising for as a light source for optical communication. And again, you know, we all know that if we have, you know, quantum wells, we probably with, you know, this wavelength band gap towards in 1.3, 1.55 micron, we actually can use them for detector to actually towards the telecommunication band as well. So we grow an NIN sort of indium gallium arsenide indium phosphide quantum well structures and making them into photodetectors. And look at that, we are able to achieve very high responsivity at both 1000 nanometers as well as 1.55 nanometers. So this is a very nice results, and for this wavelengths based on quantum wells, and also we can show that we have quite good modulation speed from those nanowires. So basically, from here you can see that quantum wells in nanowires have very lot. We are able to actually grow very nice quantum wells in that. So that will actually form a good base for a series of other devices. So in the future, what we would like to work on is actually trying to further improve our nanowire LEDs, so that to seek their application for integrated like light source for integrated photonic system or for life applications. We also want to explore the fundamental importance inter-subband transition for the mid-infrared or long-infrared wavelength photodetectors. And certainly, you know, for the very fast-growing and developing quantum technology, we want to also explore whether we can actually look at nanowire-based single photon detectors, especially for those ones working at telecommunication wavelengths for the quantum technology. And because of this, you know, one-dimensional nature of the nanowire, the large surface area, the very, you know, gentle sort of mechanical force with the substrate, you can actually make them into flexible device. We can also use large surface to making sensors for the bio and medical applications. So we see there's a lot of important application for nanowires in various fields beyond optoelectronics. And then finally, I just want to also mention that in Australia recently we have established a new Center of Excellence on the Transformative Metal Optical System, which is actually a big research center composed from 5 Australian universities in collaboration with more than 20 universities across the world, trying to develop the next generation miniaturized optical systems that are based on, you know, nanowires, metal surfaces, a series of other optoelectronic devices to be able to generate and manipulate and detect light for the advanced optical systems. So we're also looking forward to a collaboration with you and a lot of researchers in India to really contribute development with future different technologies in holographic displays, night vision, optical sensor, LiDAR, infrared quantum technology, as well as Wi-Fi technology. So I think I'm probably already exceeding my time, but I just want to conclude by just saying that I hope I can convince you that 3.5 semiconductor nanowires offers great potential optoelectronic device applications, and it's very important to understand optimized nanowire growth and characterization, as well as device fabrication to achieve high performance devices. And thank you very much for your attention.
Thank you, Professor Lang. It's indeed a very nice, motivating lecture. And we also have Professor V. Ram Gopal, distinguished professor, our Director of Indian Institute of Technology, Delhi, as well as our IEEE Hyderabad Chairman, Mr. Srinivas sir here. And it's open for questions from panelists. If there are no questions, then we will move forward. And we extremely thank Professor Lanfu for her time in giving us a good lecture on this semiconductor optical nanowires. And we look forward to continue our collaboration with you for the chapter activities and other activities as you mentioned. And I also request Professor James, the IEEE NTC President, to share a few words, and then we will proceed with our regular section.
I have really enjoyed the 2 talks so far. Excuse me.
Thanks.
but it's getting late here, and I'm sure Professor Lanfu will commiserate with that. I will leave at this point, but I've enjoyed the two talks so far, and we'll look forward to contacting Dustin Gilbert because I think he's got a lot to offer, and I don't think we've trapped him into NTC yet, but that's to come. Okay, thank you.
Thank you, Professor. And Professor Balasubramani, you want to share something?
No, I just wanted to thank Professor Lanfu. It was a wonderful lecture, and we are very, very happy to know that it has so much of application, in LED and fiber optic, communication and all that. So really, we are very happy, and thank you very much for a very wonderful lecture by you. Thank you.
Thank you. And also,
thank you.
Thanks for Jim for staying on for our talks. And I'll see you tonight.
Well, I'm not as extreme in the early morning as I imagine you are. So, so everything is relative, right?
Yes.
Thank you.
Okay. Thank you very much, everyone.
Thanks. And over to you, Khalid, then we will have our Hyderabad Section Executive Committee address. Over to you, Khalid.
Yeah. Thank you, Professor Lan. I hope everyone could benefit from the methods you discussed of how semiconductor wires can be used in optoelectronic application. Thanks again for joining in as our speaker.
Thank you very much for everyone attending the talks. I really appreciate it. Thank you.
Thank you, Professor.
Justice sir, you want me to make you a presenter?
No, I do not have anything to present. I just want to just initiate the proceedings if it is time. I thought Brajesh was also there, right? The session of Brajesh is over, or?
Yeah, he could not join us for some reasons, and he has conveyed his greetings for the chapter and for this activity, upcoming activities. Yes.
Okay, so then we are good to go ahead with the section proceedings right now?
Yes, sir. Yes, sir. We are good to go ahead. Yeah, we are on time and we are good to go ahead. Thanks.
Okay, yeah. Welcome all. It's indeed a great moment for Hyderabad section to start Nano Council for us from Hyderabad, and appreciate all the efforts of Santhosh in this regard. Like he has been following up with us, reached out to all the members who are there, who have been part of this Nano Council, and then that is how we enabled the petition and got this council going. It's a great effort in that direction because at chapter we are growing in terms of the areas, the current chapters which we have. Apart from that, we have included new chapters that have come in. Basically the robotics and sensor, where we find a lot of applications of nano into those areas. Apart from that, we already have this PES, IAS, PLS, photonics and MTT, computer society, CIS, CAS, EDS. So where, I mean, applications of nano technology can be leveraged to a great extent, and then kind of bring in those advances to come up with new applications in these domain areas. So in that regard, I think it would be a very good add to the section wherein we can have a lot of collaboration with all the other chapters which we have. And congratulations once again, and welcome on board with the chapter. And yeah, the very interesting set of topics have been lined up for these 2 days. And again, would thank all the speakers who have been kind enough to spare the time and be part of this inaugural as well as 2-day talk which we have planned, though virtual, but I think it would have been a great event if we could have joined in person. Yeah, but given the situation and the constraints we are in, I think we will leverage whatever best is possible or available with us at this point in time. And again, thanks for the very great lineup, Santhosh, and appreciate all your efforts. Yeah, let's go ahead and take it forward on this one. All the best for the chapter activities as well as for the 2 days. I think it will be very exciting 2 days for individuals who are directly working in the nanotechnologies to hear them what is going on, and then how, I mean, I would be more interested when we can collaborate with our other chapters who are there in those domains, and how nanotechnologies can be leveraged into coming up with applications which are like new advances in those domains typically. Yes, nano by itself is having advances, but the cross application of that into the domain space and coming up with the solution in those domains, I think that's a win-win for all of us, like kind of. So on that note, I think I would say this is an excellent opportunities for the exposure all of our student community or the professionals they would get through the activities which Dr. Santhosh has planned in the lineup in the next 6 months. So again, would appreciate all of them to keep a watch on that, and then leverage whatever talks or webinars that are being planned and being enabled for use of all the student community as well as the professional community. Yes, on that note, I would like to conclude this one and hand it over to Santhosh.
Yeah, thank you, Srinivas sir. As well said, we have a good support from the section chapter, and thanks for all the support and the team. And we will make sure that, as you said, and Professor Dustin and Professor Lanfu also said, that we will collaborate with the chapters and we will see how we can take it forward. Yeah.
Yeah, that's great. Yeah.
Thank you.
Yeah, Balu sir, you want to go ahead?
Yeah. Thank you, Dr. Santhosh and Mr. Srinivas. It's really a pleasure, that we are having this council chapter, nanotechnology, and having heard, Professor Dustin and Professor Lanfu, it appears, how all pervading is nanotechnology. So everywhere, he was. In fact, Professor Dustin was talking about, even energy, photovoltaic and wind energy also, the blades and all that, how nano coating, is such a fantastic thing which is happening. And Professor Fu, has talked about, the LEDs, and as a source for fiber optic communication. It's really very fascinating, and it is highly interdisciplinary, and we are extremely happy. And in fact, this nanotechnology council has got 23 societies. I don't know. Probably it includes most of the societies, and it's really great. And it is really an upcoming technology. And in fact, we have been talking about 4Gs, 5Gs and all that, and then I think the 6Gs and 7Gs, and I think maybe only definitely they will be on nanotechnology, and it is going to just get into everything, and then we are going to make use of it. Only thing is, as we keep on becoming more and more this nano, and so on and so forth, we have to be having so many regulations also. And then even in the medical field, how it is getting used so much. We are very happy to know about that. And then we are very, very happy that we are having a full one-day session beautifully, with so many keynote addresses and all that. And we are next going to Professor Ram Gopal, Director of IIT Delhi, and then we have our own Dr. Amit Kumar, and then of our section, past chair, and Dr. Vijay, scientist, GE of ARCI. That is a beautiful, and he is the head of Center for Nanomaterials in ARCI, which is under DST, and it is really great. They are situated in Hyderabad, and I'm sure IIT Hyderabad and ARCI and many other organizations here, we can work together, and then many of our students will be very keen on doing this. And we are going to have Dr. Suryanarayana also from IIT Hyderabad, and then Sivaramakrishna from IIT Hyderabad. So IIT Hyderabad has got a lot of people, who are doing a lot of work in this area, and so we would be very, very happy. And then we are also having one product engineering value momentum. So, and how this is coming into nano computing also, quantum nano computing. So we are going to have Mr. Bhagwan Komadi. That is another great thing, you know. I think so many people are there in Hyderabad, and IEEE being the leading organization, you know, and we can all cooperate, and all our societies, we will work together, as Mr. Justice Srinivas has told. We will work together and make it a grand success. So let me congratulate Dr. Santhosh and our council chapter, Nanotechnology Council chapter, and all the volunteers with this. And so let us go ahead and make it a grand success. Thank you very much for giving me this opportunity.
Thanks, Professor Balasubramanian. It's very indeed with all your experience, and we look forward to take this chapter to greater new heights. As you have rightly said, this is a planned with many activities, and we will make sure we will also work ensuring in the policy making to get into this nano step. Thank you, Professor Balu. And we have Professor Arifuddin.
Yeah, good morning, everyone. I hope you can hear me, Santhosh.
Yes, Professor.
Yes, sir. Loud and clear, Arifji. Go ahead.
Thank you. A very good morning to all the dignitaries present here, all the participants of today's Nano Day celebrations, the inaugural of the Nanotechnology Council of IEEE Hyderabad section. I am really pleased that we had the presence of Santhosh at the R10 level with young professionals, but the way he has taken this initiative in establishing the Nanotechnology Council at Hyderabad section, I would really appreciate his efforts. We already had most of the societies here in the section, but we wanted someone to come forward and take this responsibility, and Santhosh has really, risen to the occasion, and congratulations to you, Dr. Santhosh, for doing that. And we are all with you in this efforts. And what we would like, this is from my own perspective, how we would request you to take this forward is to encourage research among our undergraduate and postgraduate students. Definitely PhD people, they are already doing into research, but undergraduate research is also a very important component that has taken off in these times of pandemics, with students having access to a lot of online resources. So we will, I request you to plan certain events in which we can look at the research aspect in nanotechnology for both undergraduate and postgraduate students. And they should come out with publications. Just let me share with all of you that we are organizing 6 international conferences this year and the next year. We have the Humanitarian Technology Conference, which is being organized by the Hyderabad section in 2022, and 5 technically co-sponsored conferences. So, with such good IEEE conferences, we definitely need good publications, and that should also come from our own section. And we already have good presence in research, but with Nano coming into the picture, I believe there should be one separate track for Nano, in all these conferences. So that kind of initiative is requested from you, Dr. Santhosh, and your team. The next thing that I would like to draw your attention towards is conducting of FDPs. So it's really a great effort that you have planned today's full day session. But if you can in future also think about conducting FDPs and promoting this activities of nanotechnology, because it's kind of the train the trainer programs, and let us not just restrict to the theory sessions. Wherever there is a possibility of conducting an online session for hands-on, let us say if we have got some tools. I know we are restricted by tools which are really very costly, like ComSol, multiphysics and stuff like that. But if there is a possibility of exploring open source tools, if there are any, because at least from my side, I'm planning to organize SOC design workshop using open source tools from Circuits and Systems Society. So definitely there are tools, we just need to look into that aspect and explore. And finally, we should take this towards some kind of a project competition. So in order for this whole thing to fructify, if we can plan a project competition for various colleges, various student branches, that would actually leverage and bring about nanotechnology in every aspect. So once this is happening, I'm not too sure whether at the student branch level also, I think we can have nanotechnology chapters established. So that will actually, bring all these societies, even students from different departments together. Right now we have computer society in the computer department, CAS society in the electronics department, PS in the electrical department. But if we have a nano society and all the department students get together, I think that's going to be a real wonderful assimilation of all the engineering branches into one. As I am also the chair of Robotics and Automation Society, the interim chair for now, I feel that there are very good opportunities for nanotechnologists to collaborate with robotics and come out with really good products and innovations, and so we can actually encourage that in a very nice shape. And specifically speaking with regards to COVID-19 pandemic, so we have plenty of opportunities looking at solutions with respect to the COVID-19 issues. So we can try and encourage some kind of a hackathon or some kind of an innovation driven event where we bring out solutions with this. And finally, I would also like to thank Professor Ram Gopal Rao sir, director of IIT Delhi, because the last time I had interacted with him, he was in Osmania University for one of our workshops in 2017. At Osmania University, we had conducted a international conference, IEEE International Conference, and he had personally come down on the invitation of Professor Chandrasekhar, and a wonderful talk was given by him as the keynote speech. So I have the privilege of listening to him once again. So your presence here is really encouraging, Professor Ram Gopal Rao sir. And we also have our eminent personalities, Dustin, Lanfu, and all the speakers who are lined up for the day. On behalf of IEEE Hyderabad section, as the secretary, I would like to take this opportunity to thank all of you for dedicating your time and efforts. And I hope that this is going to be a real great start for the Nanotechnology Council at IEEE Hyderabad section. Thank you so much, and all the best to you, Santhosh and team. Thank you.
Thanks, Professor Alifuddin. It was indeed a very broad perspective. I collected all your points, and yes, we need to involve all the student branches. And just for information, we recently had our IEEE Nanotechnology Council student branch established at Vardhaman College of Engineering, headed by Sai Prasant, our student council representative. And we are also planning a couple of other student branches, want to be at IIT Hyderabad and other places. And thanks, we will also execute the projects, open source projects, which you said has a real value, and we will get undergraduate researchers to publish in our own conferences we have. Thanks for a very brief, and all the points are noted, and we will come up with definite time. And Professor,
Santhosh, I have a comment to add to what Dr. Arif has mentioned.
Yes,
I
sure.
think as a chapter, we need to have our own goal as to down the line 1 year or down the line 2 years. What is that we are going to come up from Nano? Because Nano cannot create something off the shelf right away. Like in the next 6 months, something may not happen. But if you plan some kind of a solution where maybe current problems are there, maybe with IoT picking up, the device miniaturization is one area, or the security aspects within that. Maybe one problem we may pick up, and then you may tag it to the Nanotechnology Council objectives, that down the line we will involve the students or your research team who are actually undergoing PhD with you, or any of the other colleges we are collaborating with, and come up with a solution down the line. Then I think the whole thing will get kind of successful, or we can say the fruits of all of our efforts in going through with the council or establishing that will be materialized. I think that's the way we have to guide or give the direction. I hope you can just consider those insights and then probably plan something out so that the solutions actually should come out of this section across the domains.
Yeah.
Rather than just organizing some webinars or organizing people, as Arif said, publishing papers is really in that direction, but the outcome should be really targeted. Maybe those papers are miniature steps towards achieving that objective, but I think we need to have that larger goal of what kind of solution I'm going to give to the market or to the society for use. So I think that objectives, I think it would be a great step.
Sure, Justice sir. We will work on that to do a translational research and product along with all the committees available in the section level with entrepreneurship headed by Venkatesh sir and everyone. We will collectively work there. And if we're done, I request Bala sir, the treasurer, to share his views. Bala sir, you are on mute.
Thank you, Santhosh, and it's very important that Nanotechnology Council has been started within Hyderabad section, and I appreciate the entire efforts what you have taken to get to this particular state. What I want to draw attention to everyone is the purpose of Nanotechnology Council is to ensure that we advance and coordinate with the different fields which are amalgamating and coming out together as part of nanotechnology. And it is important that we drive our education functions and technical functions and also the important areas of investments associated to the different societies which are contributing. I believe 23 different societies are coming together to form this nanotechnology council, and their contribution is very, very critical. And it is important that we bring that kind of a research functions and to the visibility and make it published as part of the IEEE transactions of the nanotechnology council. The more we do, the better visibility what we create, and it is important that I draw your attention to also effectiveness of this particular technical activities through the different committees like nanomaterials, nanoelectronics, and nanobiomedicine, which is going to make an important element of our investment. So my request is start focusing in building such kind of a committees and bring that visibility to the entire section and make it as part of the global scale visibility of our members. Further to that, also focus on some of the important standards associated to the nano, which will make a tremendous impact. So with that, I wish all the best for the Nanotechnology Council inauguration. All the best wishes.
Thank you, Bala sir. Thanks. We will make sure that all the points are covered, and we will represent the section in the global audience. Thank you. And followed Professor Shiva Sharma, you are there?
Yes, he's there.
Yeah.
Yeah. Good morning, good evening to all the distinguished panelists and participants. In fact, let me congratulate Santhosh and team for taking up the initiative of forming an NTC chapter at Hyderabad section. I know Hyderabad section is very active with several societies, but this is another feather in the cap in terms of showing engaging the members of the Hyderabad section in various important aspects. In fact, morning Professor Dustin's lecture was very inspiring. In fact, even at the age of now 57, I feel like, can I start my research career, restart my research career? That it was so inspiring, and so many kind of applications he was narrating. I'm sure, in fact, I was going to the NTC website as well. So this is the 8th chapter within India, and out of which there are 16 chapters in the entire all regions put together. So that means about 8 chapters are there in the India itself. Now it is, in fact, it is a highly interdisciplinary area. In fact, it is the area of nanotech NTC is overlapping with many other societies, and possibly the NTC chapter can take a lead in terms of engaging the student members. In fact, in terms of the professional members, in terms of the student members also. Just I was going through the annual report of 2020 that was shared to all of us. We have as the second largest professional members and the first largest student members in India. So obviously, this being a very important, this nanotechnology is an upcoming area where it's intervening with all the aspects of human life, be it medicine, be it automation, and several other aspects of it. Possibly this NTC chapter will make it very vibrant and engaging the student members and the professional members, especially as Jasti has mentioned, collaborating with other chapters. I suggest Santhosh to please take the lead in collaborating with other chapters and see for the domain specific whatever our focus areas where we can jointly work together and then help the researchers and the professional members and the student members in this particular domain. I think it will go a long way. Incidentally, I thank all the Professor V. Ramagopal Rao. In fact, I remember he was the chief guest. He was giving a keynote address in Indicon 2011 when the Hyderabad section has hosted Indica in 2011, so where Professor Ram Gopal Rao was given a keynote address on the nanotechnology. Incidentally, he's a pioneer in the area of nanotechnology and a great educationist. And we all look forward. In fact, I feel that it's an intellectual feast for the people today. The kind of line of speakers who have been scheduled to deliver on this day. So I wish Santhosh and all the participants very best. And I hope this NTC chapter will make a mark for itself in Hyderabad section in the upcoming days. Thank you, one and all.
Thanks, Professor Sivasubramani. As you rightly said, we will make sure all the results met, and we will collaborate with the chapters within the scope and identify to bring in all the student branches to get it done. Yes, Justice, sir, you are telling something?
No, I'm fine. I think the overall.
This is Venkatesh here. I wanted to mention one point here. Okay, I mean, I see that recently the Telangana government has opened an incubation center for VLSI startups, and it's coming up in the new what you call T-Works and the new T-Hub place. It may be a right time if we can put together some of what we would need for the branch within nanotechnology, which is nanoelectronics, about which Professor Lanfu also gave a very nice talk. If we could generate interest in the startup area in some of these, even research that can have some return on investment, we can certainly approach the government in equipping the incubation center with some of the tools specific to nanoelectronics. So we can certainly put forward a proposal, and I can help in reaching out to the people who run the incubation center. I'm also a part of that.
Yeah, thanks, Venkatesh, sir. It's really nice to have you, and we will definitely take this offline, and we will discuss how on taking this forward. And I'm interested in getting that done. Thanks for your insights, Venkatesh. Yeah.
Thank you.
So over to you, Khalid.
Okay. Good things come to those who initiate. Thank you all for joining us today and being a part of this launch. I thank the Execom for their valuable words and glad tidings. Next,